Well, all of you know me, so I don't have to present myself. Let me start explaining the title of the talk. So I'm going to talk about the contractivity of quantum channels and their composition. So what I mean by contractivity is that if you have a way of measuring the distinguishability between two quantum states, so let's say that you have two states rho and sigma that are distinguishable in some sense. After you apply a quantum channel to these two states and you get their output states, quantum channel T, these two states can only get less distinguishable, let's say. They have to get one of them near to the other. I have to do bigger pictures? Okay. So this means that this distinguishability distance has to decrease under the action of the quantum channel. Okay, the intuition behind this is that quantum channels describe dynamics in open quantum systems, so information somehow leaks out of the system, and we are losing the power to distinguish between these two initial states. So the idea of contractivity is in this sense, the sense that the states become more and more similar when you apply a quantum channel. Or they stay the same, I mean, the distance can be preserved. So this is the idea that if we iterate over some quantum channel, T, the output state will be more and more similar if the channel is very contractive, because it contracts all of the state, and if it is not very contractive, such as unitaries, which are perfect isolated evolutions, the distance will be preserved along the whole evolution. But we don't only care about this case, but we care also what happens if we have two channels, A and B, and we intercalate them. So we have this composition. So our intuition, for instance, is that if A is very contractive, AB will still be very contractive, or if A and B are not very contractive, then their composition shouldn't be very contractive either. That's a kind of intuition, but we want to formalize the characterization of the contractiveness of a channel such that it gives us information about the contractiveness of their composition. Okay, so this is the motivation. And why do we want to do this? On the one hand, because quantum channels are present in describing noise and characterizing noise. So, for instance, there are recent papers by Franza and Garcia-Patron using theoretical results to prove bounds in what can be done with quantum computers using the mathematical description of quantum channels and this kind of contractiveness results. And also recent papers in Harper, Flamia, Wallman, about characterizing noise using the different models of quantum channels to characterize the crosstalk between qubits and stuff. So knowing more about the contractiveness can help us learn about noise. But they can also be quite helpful in the context of stochastic algorithms, where a quantum algorithm is not described by a pure unitary, but you are performing some partial measurements or some stochastic process, unitaries that are random, whatever. And to describe this kind of process, you also need quantum channels, and the convergence of this process can also be described. So a recent paper about this was by Toby Cubitt and the separative ground state preparation, or our quantum genetic algorithm, which is also a process described by a quantum channel where we have different blocks that are composed. Okay, so let's start with some mathematical definitions. First of all, a quantum channel is, so I already explained in the physical sense what it is. In the mathematical sense, they are linear maps from density matrices to density matrices. Yeah.
So, what is the difference between the first and second?
Yeah. In this case, yeah, what I mean is that we want to characterize.
It's just a channel.
Yep. Yeah. Okay, so the intuition is that I think I will introduce that shortly. So yeah, let me continue and I hold on for a minute and I will be there. So I was saying, okay, so in mathematically speaking, quantum channels has just maps that preserve the trace of the objects that they take. So density matrices which have trace 1 will still have trace 1 in the end. And they are completely positive in the sense that if they take a positive operator, they will transform it into another positive operator, even if you extend the channel to an arbitrarily high dimension. So, and how do we measure distinguishability between states? One way would be the infidelity between states. So the higher the fidelity, the lower the distinguishability. That would be one way to measure it. Another way to measure it could be relative entropy, which has a more informational meaning. But today, I would like to focus in the trace distance. So the trace distance between two states is defined in this way, where this is the trace of the absolute value of their difference, where this is not an element by epsilon element absolute value, but this other thing is the positive square root of this, but in the case of Hermitian matrices, this trace can also be, so if A is Hermitian, this is just the sum of the absolute value of its eigenvalues. Okay? So the intuition here is that we get some operator that is traceless, rho minus sigma. We compute the eigenvalues of these operators, which gives you information about the size of this operator, and we sum them up. And this gives us the trace distance. Okay, so this trace distance is 0 if and only if rho and sigma are the same, they are exactly equal, and it is 1 if rho and sigma have orthogonal support. So this means something like if we describe, there is a basis in which we can describe rho, and it's concentrated in some corner of the space, and when we describe sigma, it's in the other corner. So there is no overlap between rho and sigma. Okay? This is the intuition behind being orthogonal. If these two they are orthogonal, then the trace distance is equal to 1, which is the maximum. Okay. Okay. Why do I like this distance? So I like this distance because it defines the maximum probability with which you can distinguish between the two density matrices. It has.
Can make measurements and then can clearly recognize it with the measurement outcomes.
Yeah, that's the thing.
There is a basis that you can at least run.
Yeah. So the idea is that if you can distinguish rho and sigma with probability p only if p is less than 1/2 plus the trace distance. Okay? So this is the idea. As I told you, if they are the same, then the trace distance is if they are very close to be the same, the trace distance is almost 0. So you can only distinguish rho and sigma with probability 1/2. That is, you can throw a coin and you will get the same precision. But if rho and sigma have orthogonal supports, then you can define a measurement in the system that will assign 1 to all of these values and 0 to the others, or 1 to these values and 0 to the others, and depending on which one you obtain, you can perfectly distinguish between rho and sigma. So this somehow characterizes all the things that can be in between. Yeah? P. This would be like the probability to distinguish between the two. So if you define some protocol to try to distinguish, so you have prepared either rho or sigma, and you perform some measurements, the maximum probability that you can obtain is bounded by this amount. You cannot get better than that. Yeah, of course, but that's what I meant, that if the distance is very, very close to 0, so rho and sigma are very, very similar, this will be very close to 1/2. That's what I meant, yeah. Of course, if they are the same, you don't have to distinguish anything, but yes. Okay, so this is the kind of distinguishability property that I will care about, and the magnitude that will evolve when we apply this quantum channel. Okay? So up to now, what do we know about this property? So of course, okay, so this distance satisfies the inequality that it decreases under the action of a quantum channel, but we may care of quantum channels that are strictly contractive, which are those for whom we can find some constant, tau, that is strictly less than 1, and in these cases, any pair of states that was initially distinguishable will no longer be perfectly distinguishable in the end, because the trace distance will strictly decrease. Okay? So that's good. That could be something that we could care about. But let me move this. And so this motivates the definition of the following quantity. The tau of a channel, it's the maximum value of this contraction that we could have. Okay, so if this thing is 1, that means that we can find two, so these two are different, two different rho and sigma that have the same distinguishability level initially and in the end. So due to the properties of the trace distance, we can assume also that rho and sigma are orthogonal, initially have orthogonal support. And then, as the trace distance between two orthogonal matrices is 1, we can remove this lower term and only preserve that one. Okay, so this means that this tau of t, which is the contraction coefficient, let me see where I can write it. The contractivity coefficient is the maximum distinguishability that you can obtain from two initially distinguishable states. So we have two initially distinguishable states, I apply the channel and I get a maximum value for the distinguishability after that. That's tau. If it is 1, that means that I can find two initially distinguishable states that are still distinguishable in the end. And if it is strictly less than 1, that means that you cannot get perfect distinguishability after applying the channel. We can do the same for the minimum. And this means that even the channel is very contractive, you still can preserve some distinguishability in the end. So there is a level of distinguishability that you cannot go below that. So there are papers by Zer, Wolf, and Reeve, and also Sirac and Wolf. There are many papers with these properties and beyond, and you get nice things, such as for the composition, such that the contractivity coefficient for a composition of channels is less or equal to the product of the two contractivity coefficients, and the converse. Yes?
Contractivity depends on the state that the matrix that you are using, because you have like only a separation of a quantum channel, but it doesn't depend on the state.
States? No, because it's a maximization over all states. So it doesn't depend on the input states. So there will be a pair of states that will obtain that contractivity, but in general it's a property of the channel.
Okay.
Yep, thanks.
Does it need to exist a pair of states? That's why you use this sum instead of a maximization.
Yeah, probably.
It's the
Yeah.
least.
Yeah, I know. I mean, probably I could write just max there, but
States, but for sure, like this is the minimum.
so the thing is that, sorry, Mateus, thanks for the comment. Okay, I'm working always in finite time, as you see. So these are finite steps and also in finite dimension, which is much simpler. And probably that will be necessary for most of the things that I will say, but I didn't explicitly say it. Probably I'm using here sub because it's like that in the literature, because most of the results can also be generalized to infinite dimensions, and maybe there you need the sub. But I don't know. I don't really know. But yeah, you can think of this about the maximum. That's why I say maximum also, because it's.
I feel like the maximum necessarily exists.
Hmm? Mm-hmm.
was in fact the relative entropy.
Yeah, but this is,
the trace distance. I know the maximum doesn't exist.
yeah, but this is the trace
Some
distance.
does exist.
Yeah.
It's well defined.
Okay. But this is
I
the,
know examples of this. But is it easy to check the second inequality?
this one.
No, for the path. Yeah, the second one. Yeah.
Easy.
Is it like easy to
Go from here to there. Yes, yes. And you can even go from here to only pure states, rho and sigma pure. But I don't. Yes, it's somehow easy because, yes, you can always, this D is, so it's, you can introduce proportionality terms as you wish. So you can like dilate the rho minus sigma so that you can consider that it comes always from some two orthogonal states somehow, but yes. So the idea here is that, okay, so these are two properties that we can obtain from the composition. So if you have a maximum contractiveness, then you cannot get more than the product of the two contractions of those two channels, and it happens something similar for the minimum. These inequalities are ties. You can always find two channels that satisfy these inequalities, yes. No, no, no. No, because you can think of, so tau of A can be 1, but tau of A squared not being 1, for instance. I can give you an example later, but it's like, it's as if A is mapping things from the complete space to its range, which is a smaller subspace, and maybe in that smaller subspace, you have some, the states are no longer perfectly distinguishable after applying A for a second time. That's somehow the intuition. But yeah, I mean, I can give you an example. Amplitude damping is an example of this. Yep. Should I continue or do you want the example? I mean, I can give, okay. So this, for instance, bounds how applying the state many times can converge. So applying this inequality for the same state you know that the distance of two initial states will evolve between these two values, for instance, so between the maximum and the minimum, of course, and these kind of things. You can obtain these kind of results. And these results can also be used to, so if you have a quantum channel A that has a unique fixed point lambda A, yes, and then you want to estimate the distance between this fixed point and the fixed point of the channel AB, the distance between these two can be bounded by, and in a bit more sophisticated ways too, this distance okay, so if the distance between the original fixed point of A, the stationary state that is invariant and then the action of A, and applying the second channel to A, if this distance is very small, this means that the new fixed point will be near to the original one because the original one doesn't vary much with the other distance. If it varies a lot, then the convergence is very important. If A has a strong convergence, then it doesn't matter what B does, A will converge again towards its fixed point, so somehow will be near. So this is just an intuition, just to show that you can obtain different results from here. 1 minus tau of A. Yeah. So if it is, yeah, it explodes if tau is 1, which makes sense. Okay, so there are many examples of these things that you can tell with these things. For the amplitude, for the depolarizing channel, you can get the contraction value, which is homogeneous in a sense. The amplitude damping has tau 1, but it has a unique fixed point, and you always converge to that fixed point, which is a bit counterintuitive in some sense. The phasing has also a contraction value that is 1 because you only remove the off-diagonal terms, so things that were distinguishable in the diagonal will still be distinguishable, and many other things. So the problem here, or the limitation that we have, is that, for instance, as I told you, amplitude damping, or let's think about the phasing. So the phasing has a contraction value that is equal to 1 because if I have things that are distinguishable in the diagonal, they will still be distinguishable in the end. Okay, so the contraction is 1 because I can find two states that are still distinguishable. But this contractivity coefficient is also 1, for example, for unitaries. So we would like to have something characterizing the difference between these two things because they are not the same and they are not equally contractive. But according to the contractivity coefficient, we cannot tell the difference. Also have something similar for two states that have the same values here, but have very different behavior in between. So what I would like to have, so this is one which is the maximum value that is attainable and this is 0. Now what we have are, these are like the ones, have like values in between, tau of t, mu of t, and we would like to have some sequence of values there in between characterizing the contractivity of our channel. That's what I would like. So,
given a channel T, which can be any CPTP map, what we can define these 2 quantities, this tau and this mu. And they are giving values. How can we, I don't follow. Can you repeat?
So we have, so these are the limit, okay. So we have obtained these two values that describe the contractivity of the channel T, which is the maximum contractivity and the minimum contractivity. Okay? The problem here is that, for instance, if the maximum contractivity is equal to 1, that doesn't mean that the channel is not contractive at all.
For some states it does.
Yeah. Okay, so what I would like is, let's say, a more fine characterization of that contractiveness. And see if it is. I can tell you my proposal. So the aim was to reach there. I don't know if we will have time, but
we have time.
Yeah. No, yeah. So I am about to get there. So the idea is to obtain somehow more values there characterizing the convergence of the channel. Why? Because with these two values, the only thing I can tell about the composition is this. What I hope is that if we have more values, maybe we can tell more about the composition without actually computing those values for the composition. So let's say that A has these values easy to obtain, B has these values easy to obtain, but the composition doesn't. Still, as I have the values for A and B, I can say something about the values for AB. That's the idea. And the problem is, how do you define these values? And that's my proposal now that I am studying. Okay, so that's the idea. So first idea, okay, why don't we use the eigenvalues of T? Why is that not an option? So the eigenvalues of T have very nice properties because they are always inside the unit disk, so they have absolute value smaller than 1, which sounds okay to describe some contractiveness. But the problem is, first, that quantum channels are not perfectly diagonalizable, so you cannot always diagonalize them. And you cannot always diagonalize them with unitaries in particular. So this makes the interpretation of the effect of spectral properties of that kind quite difficult to derive for contractivity results. Okay?
How do
Okay, so you describe this map. This map in the end is a linear map on density matrices. You describe it as a matrix and you obtain the eigenvalues of that matrix. Or if not exactly. Not you can describe the channel as a transfer matrix for very big. Yeah, and still it's a linear map, so you can find its eigenvalues because it's a linear map in a finite space. Okay, so that would be the thing. But I mean, my only point here is that makes no sense because I mean, eigenvalues can be super arbitrary, and in particular, you don't get the ergodic coefficient. So eigenvalues have some relation with these constraints, but they are not exactly this. So the minimum eigenvalue and the maximum eigenvalue won't give you the contractivity coefficients. And in particular, the eigenvalues are also complex, which also yields the question, okay, what do you do with that phase freedom? And I don't know, if you want to know more about the eigenvalues problem, you can also go to Wolf and, yeah?
It does, right? Because like that's kind of a textbook thing you can find in linear algebra. When sometimes they try to, this is very silly, but when they try to kind of motivate the definition of eigenvalues, it's for you to compute like the product of a matrix many times.
Yeah.
And then they use these eigenvalues to show that if you have like I don't know, let me remember, but it's something like this.
Yeah, it has some very nice properties, but in particular, the problem with these kind of things with eigenvalues is that I can give you details later, but there appear so many things and subtleties that makes it not very useful to study these kind of things. Because the thing is that the eigenvectors of A and B could couple in many different ways. So in the end, the value of the eigenvalues is not that important, but the coupling between the eigenvectors of A and B, and that becomes really tricky when the eigenvectors are not orthogonal because they don't need to be orthogonal because the channels are not diagonalizable. You know, that's an issue, and you get similar issues with the. Hey, welcome. With singular values. Okay, so if you think, okay, eigenvalues won't give you the solution, what about singular values? So singular values are really interesting because they are used to describe the relations of linear maps in Euclidean spaces and stuff, but the problems are, on the one hand, that quantum channels don't need to be contractive in Frobenius norm, which is the norm that is related with the singular values. So this means the singular values of the channel can be larger than 1 in particular. So, I mean, how do you interpret that in terms of contraction? I don't know. And also, so that's the main problem. Singular values can be larger than 1, and they are also not very clearly related with these two values. So I want to find another possibility. And the possibility I found is related with the following game that I want to explain, and I want to finish with that if it's possible. Okay, so let's consider Alice and Bob are playing a game. Okay? So Alice will send one of two pre-agreed states to Bob. Okay? These two states have orthogonal support in that sense. So they are perfectly distinguishable. Alice will take one of these states and it will send one of them to Bob through the quantum channel T, and now Bob will measure and will try to guess, was it rho or was it sigma? Okay, that will be the game. Bob wins if he guesses. Alice wins if Bob doesn't guess. Fine. Okay, if both of them, no, if Bob is able to make an arbitrary measurement, so he's free to choose over any measurement of rho and sigma, then his probability to win is given by that. Okay? It's given by the distance of tau of t. This is the output state for the input rho and the output state for the input sigma. Sorry if I'm writing too small, but yes.
Does Bob know
Yeah.
rho, sigma, and all the properties of T.
Yeah, T is known for both for Alice and for Bob, and rho and sigma now they are given. And the nice thing will be to see how to define rho and sigma. Okay, so yes, both Alice and Bob know all of the properties. The only thing that Bob doesn't know is which state Alice exactly sent. Okay, so now if Bob is given the freedom to choose, what will be the probability of his success? It will be given by the contraction coefficient, okay? Because if Bob has the freedom to choose between two initial states, he will choose the states that preserve distinguishability the best, which will give him this value. But if Alice is given the freedom to choose, she will pick the lowest distinguishability coefficient, whatever thing, okay? Yeah, so that, okay, they are initially distinguishable, but I deceive you because now they are not. Okay, those are the two extreme cases, where Alice is given all the freedom or Bob is given all the freedom. Now we will think about a strategy so that Alice and Bob agree something in between, and that in between will give us values here. Okay, let's see how we do this. Okay, so we will let Alice fix J different measurements the following way. So Alice will choose observables M1 to MJ, okay, and such that now Bob has to choose rho and sigma, giving the same expected value for both measurements, and still being orthogonal, of course. Okay, so Alice will choose J observables, okay, and that fixes that Bob has to choose from the set of states that are giving the same expected values for those two observables. Okay. What?
So M1 to J
are observables?
Observables are prediction operators.
Yep.
And Max is not, and Max is in the equation below, are just like measurement operators. Okay, so they're the same observables.
They are the same observables, yeah. So Alice decides the observables, and now Bob decides the state, but constrained to this condition. So the idea is that
J is like answer B?
J is, let's say J goes from 1 to the dimension of the Hilbert space square minus 1. Okay?
So it's given by a channel.
It's given by by me, who is defining the game. So the funny thing is that depending on the J that you choose, you will get one of these values. So if you choose J1, you will get one of the values, and that's the thing. So the thing is that, so if Alice is given this freedom, and Bob now has the freedom to choose the state, but constrained to this condition, then the best thing that both can do is
So they are observables, not POV.
yeah, that's it. They are observables. Observables that could, in principle, not be even independent. They could even be the same observable, but that would be silly for Alice, because Alice has the freedom to constrain degrees of freedom on the choices that Bob can make. So let's write it. So this M1 to 2, J. So this is a bit small, sorry for that, but I will read it in a moment. So this quantity is is related to the probability that Bob has to guess the original state. So Alice will minimize overall her choices on observables, which are emission matrices in the system, and then Bob, constrained to these observables, will choose the two states that maximize his probability to win. And this will be the contraction value J. Okay, this is my proposal.
Okay.
What's the funny thing? So if we set J equal to 1,
But what is the goal of the game now?
what is?
Yeah, because initially the goal of the game was for Bob to distinguish between the two states the best he can.
Yeah.
So in the end, he needs to, all he needs to do is to come up with the measurement device that does it.
Yeah.
Basically. And now, like Alice,
Yeah. So the
place some constraints with this.
So the thing is that originally the problem was that Bob had to find the perfect measurement set, the perfect POVM to distinguish between rho and sigma. But now we give that given for free. So Bob can, for any rho, sigma, and t, he's able to find that POVM. He's able to meet this maximum probability. Let's say that.
Okay.
And now the game is to decide rho and sigma, and to agree on rho and sigma. That's the game. And their cards are. So Alice can choose measurements, Bob can choose the states given those measurements. If both of them play the best that they can, Alice will try to minimize, and Bob will try to maximize in their degrees of freedom.
But if you have a complete set of observables, then you have the same value to find that rho is equal to sigma.
Sorry, I realized about a detail after my introduction, but yes, please. What?
So you have a complete set of observables.
Yep.
But I mean, you have a complete set of observables, and then you impose that two states have the same mean value for all of those observables. Then the state is unique.
Yeah. Yeah.
So this is the reason we are removing one dimension of the total set of observables.
Here I am removing one dimension. Yes, that's the idea. Because if I said, yeah, if we give Alice enough freedom, she can fix that rho and sigma are the very same state, and that cannot be because the game makes no sense in that case. Yes, that's the idea. The idea of this limit is that, okay, and it can also be the case where we fixed a single. We give no freedom to Alice, okay? That could be the case. So Alice cannot choose any observable. That would be like J0. So this is a small detail.
And then the game is the same as it was before.
That's the thing. So if Alice cannot choose any measurement, J is 0, this part is removed, and Bob has complete freedom to choose rho and sigma. So if J is 0, K1, which is the first, let's say, contractivity value, it's equal to...
Then it's different, because in the original game, rho and sigma are fixed, and you want to know the maximum probability of distinguishing them.
Yeah.
And now in this new game, like, you can choose the states.
Yeah, and that's...
Maximize the game, so I'd say these two games are different.
Yeah, that's the thing. The second game is the important one. The first game is, we assume they are... The first game was just an introduction for the second game. So the real game is to choose rho and sigma, and how they choose is the game, in sense. Okay. In the end, the game is just an abstract way of defining these values, so it's not that important. The important thing is that the intuition is that if Alice is given no freedom, then this minimization is out, and we only have a maximization over all states that are orthogonal. So this yields the first contractivity value. But if we give Alice almost all the freedom to fix as many observables as he wants except for one, then Bob has no freedom at all, because there are only like there is only one direction in the difference between rho and sigma that is free for him to choose, let's say. So he has not real freedom, okay, let's say. Then we can substitute this thing by a minimization over all rho and sigma. Okay, just believe this. The thing is that if you fixed all of the observables except one, so that they can still be different, then you get a minimization over all rho and sigma, and you get the last contraction coefficient. Okay?
One question about these X.
Yeah.
So are they projections of one single observable, or are they, because then I don't really get this with this D squared. They are really Hermitian operators. Then
Yep.
it shouldn't be like J goes to D squared. Or
Yeah. Let's think. Okay. Let's think about in the qubit case. For instance, D is 2, D squared minus 2 is 2. So you can either fix no observable, only one observable, which would be sigma x, only two observables, which could be sigma x and sigma y. And you have the freedom in sigma set. I don't know if, okay, so this is the intuition. But I mean, this final value is not that important now. It's important in proper sense, but it's not that important now. The idea is that there is some maximum value of observables that you can fix without strictly fixing rho and sigma to be the same. Yes? I don't know if I understood the question, maybe.
Yeah, I was just wondering, are these M's Hermitian operators,
Yep.
or are they projectors?
They are Hermitian operators. Yeah. They could be projectors too, but that's a subclass. Maybe you can even constrain to only projectors, but I don't really know. Okay, thank you. No. So, okay, I can maybe just take 5 minutes more to. So why is this interesting in the first place? Because this definition is very similar to Wieland's minimax principle for singular values. So for singular values, you can define them in a similar way, where the minimization is over, instead of having observables, it's over subspaces of some vector space, and the maximization of over vectors that are in that subspace, and you find their contraction in another norm with another measure of distance, let's say, and that. So it could be funny to have a generalization of a Wieland's result. No, but just that. No, that's nice, because this kind of minimax principle gives some results in the product of matrices and so on. So if it could replicate those results for singular values, but for this kind of contractivity values, they would be super nice. But we are still not there. We just found this definition that somehow makes sense. And we found also that for qubits,
Then what do you want to prove, like precisely? What kind of properties you want to prove for this K?
So for instance, for singular values, we know that the singular values. So now A and B are arbitrary matrices, okay? I'm just copying a result from Bathia. So we know that singular values are constrained this way. J. So for instance, we have that the product of all the singular values from 1 to k is less or equal than the product between the singular values from 1 to k of A times the singular values from 1 to k of B, for instance. You know, these kind of things. And we also know we have things that lower bound this singular value, this product of singular values, but with pairs of products of singular values of A and B, but in opposite order, let's say. Okay? So these kind of properties would be nice to have for these values. Because then if we can characterize these values for A and B, we can find bounds for the eigenvalues of AB, for the contractivity values of AB. This would be like the target, but I am not here yet.
Why you're defining this the way it is, because you want to kind of.
We want to get here.
These properties.
We want to get to these kind of properties.
I see.
So that if most of these contractivity values are very close to 0, but there are some that are close to 1, for instance, you are blind to this property only using these two values, but you can see them in this spectrum, and this can tell you a lot of information about what can you do with that channel, mostly as an algorithm. Okay, so for qubits in particular, it's somehow straightforward to find these values. Are the singular values of the part of the channel that's constrained to traceless operators. And so in those cases, we have these kind of results for these contractivity values for qubits, because they are the singular values of a submatrix, which is easy to compute. But I think it's...
For qubit channels? So you're saying like this property?
These values for qubit channels, they can be found. Easy, it's somehow straightforward.
But then does it hold this kind of property, like this
yes.
Submultiplicativity?
Yes, because, okay, so yeah, I don't want to enter here because it can take a bit more time, but I can tell you now if you want. So, okay, so...
Because then, like, what you want to do is kind of holds for qubits, at least. That's what we're saying.
Yes, that's the nice thing. The problem is that it doesn't...
Is it something that is proven already, or is it something that you realized yourself?
About what?
This submultiplicativity of this new constant.
So I haven't found these constants anywhere.
No, I know.
So I don't... Yeah, so the submultiplicativity...
Yeah, but then, like, you realized that for qubit channels,
yeah, but
this submultiplicativity holds.
But I didn't realize from thin air. There are a lot of papers about qubit channels.
And this is known already, like this property.
I wouldn't say, but it comes from the literature in a quite straightforward way if you are looking for those values. If you are not looking for those values, then no, you won't find it.
You defined it yourself.
Yeah.
This K doesn't exist.
Yeah, but the thing is that it comes quite straightforward for qubit channels. So for qubit, I can tell you now.
Yeah, but it doesn't matter. This is a nice result.
Yoo-hoo.
It doesn't matter if you come in straightforward. You make a definition of a game, and you define this contractivity index, and then you do.
Yeah, but in the end, for qubit channels, it's not so interesting because...
Obviously, it's interesting. It's the most interesting case.
It's the most interesting case. Yeah, no. So, let me summarize. So, with contractivity...
But then right after the condition you found, like the property of this K, then you know it holds for qubits. Write us the condition that you found for this K.
It's...
What is the condition? How do you write it?
Okay.
For channels instead of like matrices?
No, but it's the same, but with the matrix that is the reduction of the channel to the traceless subspace. Okay, so we have a qubit channel. We can describe its transition matrix as this thing, where okay, so the elements of this matrix are the elements given by the inner product of the image of the Pauli matrices and the Pauli matrices. Okay, so you compute this trace, this thing, and you get a matrix that has this structure.
Wait a second.
So this is I am saying only one thing. This is 1, and here there are 3 values. Okay, this is 1, 3.
T can be any single TP map.
Yeah, in qubits. Yes.
And like sigma j's are the Pauli.
Yeah.
And then what is delta and what is UR?
What is U? Well, this is V, but yes. V bar is a vector column 3. Yes?
this is now only a single qubit, right?
Yes.
This is for a single qubit.
Then what is the relation between these T hats and the channel itself?
If you want to, for instance, if you define out now a state of a single qubit in the polar form,
Okay.
yes.
Yeah.
Now the image of this
Okay.
yes, because of this property. So the idea is that if you have the distance between, now say that sigma is the same but with a vector s, so I'm going fast around this. If this is the original distance, the final distance is this b cancels out, so you only obtain this. These bars are the Euclidean norm of the vectors, three-column vectors R and S. So here, as you are obtaining this thing, in the end, the definition of these contraction values yields the definition, the minimax valence principle for singular values of the submatrix delta. Okay, this is the idea that as you have this property, then you can, in this case, it becomes a singular value problem. Only in the qubit case, in more general cases, it doesn't. And now that you have this as the product of, let's say that, so a product of AB will be something like something here or here, delta matrix for A and delta matrix for B. Okay? So now this should be, I mean, it doesn't matter, but I will get confused. Okay, this is the singular values of A, B, and now you can relate these things with these things via this thing.
Okay.
That's the idea.
Okay, and what is the inequality for the heat K, J, and B? How does it relate?
So for instance, K1 has to be semicolon K1A, K1B, which is this, but we can also lower bound by the maximum of, I think it's by the maximum of this combination. So either you pick the maximum of A and the minimum of B, the minimum of A and the maximum of B, or the middle contraction coefficient of both, and all of these are bounding this value from below. So you can compute these three, and the maximum of these three gives you a lower bound on the value of the composition.
You have nice results already. I like these inequalities.
Okay, so thank you very much for listening. I think all of us are hungry already, and thank you very much for the curiosity and the value, and we can discuss this.